So now let's continue with the medium line model. Medium lines are considered those lines which are above 80 kilometers and below 250 kilometers. We will use the nominal pi model as shown in figure 5.4. Here, unlike the short line where we neglect the shunt capacitance, here we cannot neglect the shunt capacitance, so we consider two admittances, one at the sending end and the other is at the receiving end. The admittance y is given as a complex number. It has a real part, which is the shunt conductance, and the imaginary part, which is JWC. The shunt conductance can be neglected since it represents the leakage current over the insulators and due to the corona. So if we neglect these shunt conductance, we will end up with only an imaginary part, which is JWC times the length of the transmission line. C, as we have seen in chapter 4, is the line to neutral capacitance per kilometer, and Al is the line length. So here we can see that if we want to calculate the voltage at no load at the receiving end, we can apply the voltage divider law. So it is the impedance at the receiving end divided by the sum Z plus this impedance times Vs. It will give us the voltage at the receiving end at no load. So based on this nominal pi model, let's write the equation for IL and Vs and Is. So IL is equal to IR plus Y divided by 2 times VR, while Vs is equal to VR plus the voltage drop in the transmission line, Z times IL. Let's see the expression of Vs now. It is 1 plus Z Y divided by 2 VR plus Z IR, while Is equals IL plus Y divided by 2 Vs. By substituting IL and Vs, we can end up with equation 5.19. Is will become Y times 1 plus Zy divided by 4 times Vr plus 1 plus Zy divided by 2 times IR. As you can see, equation 5.17 and 5.19 can be put in the matrix form, where A is 1 plus Zy divided by 2, B equals Z, C equals Y times 1 plus Zy divided by 4, and D equals 1 plus Zy divided by 2. So given this relation, we can obtain the expressions of VR and IR in terms of Vs and Is by simply inverting this matrix. Here, the particularity of this matrix is that its determinant is equal to 1. So the inverse of this matrix is D minus P minus Ca. So we have here two equations that will allow us to calculate Vs and Is given Vr and IR, or Vr and IR given the voltage and current in the source side. So in next part, we will solve the problem for medium line.